Oh, it automatically launched it. All right. Okay, hey guys, welcome back. Sorry about that little trouble with Zoom. I'm glad that you all made it here okay. I am going to go ahead and turn on the document camera and we can get started. So today, we're going to talk about applied optimization. Real quick, I want to actually, let me pop something else open. Give me just 1 second here. So I think there was one more student teaching thing that we were hoping to do before the start of break. Oh no, let's see, are we good? What was there? 4. Oh no, we're good, everything's Gucci. But then Katie, your student teaching was scheduled to be on the 15th, which would be the day we come back from break. And since that is going to be the day of our test, we will have to push that. But just send me an email or a Canvas message and we'll make some arrangements. The other thing I wanted to say to everybody is I still need you guys to come by for at least some sort of check-in on your honors project before spring break begins. I just want to know where you're at, what research you've done so far, where you're thinking of going with these things. It's not anything to scold you or make you feel bad if you tell you haven't done enough or anything like that. It's just to kind of give you a little nudge and make sure you're getting started. Because it is really important that you get started. These are relatively large projects and you don't want to rush them at the end. If you do that, they won't come out well and that would be sad. But with that done, we can go ahead and start on the material for today. So this, of course, is MAC2311, section OH1. It is a lecture. And today is the 3rd of March, 2021. Today, we're going to talk about applied optimization. This is section 4.7, and it's the last bit of material that's on exam 2. So on Friday, we'll do a review. Friday is the last class day before the test. The test is the 15th, which is the day you come back from your spring break. And so this being Friday being the last lecture day before your exam day, it will be our review. So please make sure you bring a note. Bring problems for review this Friday. That will be our exam 2 review day. All right. So applied optimization, what is this shit? Do I have any ISE people here? Anybody whose major is industrial systems engineering or just industrial engineering? Maybe, maybe not. See here. Oh yeah, Kevin. Kevin's an ISE guy. Oh, this Zoom update is cute. I see what they did. Yeah, so ISE, Applied Systems Engineering or Industrial Systems Engineering, your bread and butter and frankly the toaster and the knife and everything else is going to be applied optimization. Applied optimization means we're going to take, essentially they're min and max problems, but they're real world min max problems. I actually have a friend, a couple friends in the research community at UF who are ISE people. And every time I look at one of their problems, it always kind of reminds me of this moment in Calc 1. It's cool. Of course, none of those problems are vastly more complex than the ones we're going to solve in class. But think of this as an introduction to industrial systems engineering. Basically, what you're doing is you're trying to find ways to do shit efficiently, right? So like maybe I only have so much fence and I want to build the biggest pasture I possibly can. Or maybe I have, I need to make an oil can of a certain size, but I want to use as little material as possible in order to minimize the cost. Shit like that, where you have some sort of thing you must do, and you have some sort of constraint, and you want to do the thing in the most efficient way possible, subject to that constraint. And the way it works out is you're looking for absolute mins and absolute maxes. You're going to take some real world situation, you're going to write some equations down, and then you're going to try and find the absolute min or the absolute max of one of those expressions. Just for gits and shiggles, let me show you the bit of the textbook here. We'll solve some of these problems. As they do for related rates, you remember section 3.9, the other kind of real world physicsy section that we've covered. They have a little 3-step algorithm here, and you'll notice a lot of similarities. Step 1 says to understand the problem. I mean, that's cute. That's basically like do the shit. But what they mean by that is make sure you understand the objects that are being referenced in the problem. Make sure you understand what is not known and what it is that you are interested in, the given quantities, and what are the conditions. Along with that, or really along the way to doing that, you're going to draw a picture, right? Drawing a picture is usually helpful for understanding the problem. And crucially, you're going to introduce notation. So you're going to have to assign variables, just like in the related rates problems. You're going to have to like call this distance X, call this distance Y, shit like that. Once you have done all of that, you're going to recognize the thing that you need to minimize or maximize. The book calls it Q here for quantity. And then you're going to want to express Q as a function of a single variable. That's steps kind of 4 and 5 here. You'll write down an equation for like, you want to maximize the area. So you write down the area equation for whatever the object is in question. And then usually you'll have more than one variable there. So you'll need to go back and eliminate one of the variables by solving one of the other equations you have for the other variable and plugging it in. And then you're going to go back and find the min or the max, whatever it is you need. So let's do it. The farmer example here is a cute sort of introduction to these problems. So you got some dude, and that dude has some cows. Those cows need a place to be, but they can't just wander wherever the fuck they want to go. They need to be in a pasture. So this farmer has 2,400 feet of fence, and he wants to make a rectangular pasture. And that pasture goes along a river. So he's like, all right, at least I don't need to put fencing over here because my cows can't swim. We want to know, of all the ways he can do this, and they've drawn a few of them here, of all the possible ways to do this, which one gives us the most area? And they've got a few particular ways that this could be done here. If he makes it real short like that and real long like this, 100 by 2,200, that's going to give him 220,000 square feet. If he makes this like a little bit closer to square, 700 on this side and 1,000 on this side, then he gets 700,000 square feet, which is certainly more area than that. Happier cows. If he takes this to the extreme where he makes these side lengths real long and makes this side length real short, the area gets small again. So somewhere in here is a sweet spot that will maximize that area. All of these use the same amount of fence. So the question is, how do we do this? The best way to do this is just to work examples. So that's what we're going to do. So a farmer wants to build a rectangular pasture along a river using 2,400 feet of fence. Find the dimensions which maximize the area of the pasture. So she wants her cows to be happy, wants her cows to have lots and lots of space. The best way she can do that is by taking a calculus class, learning how to find mins and maxes. Naturally, every farmer does this. They enroll in 3 years of algebra classes and then follow up with a calculus class to make sure they have the happiest cows possible, right? What farmer wouldn't do that? So our first step here is just going to be to draw a picture. Here's my river. And here is my pasture. I know I don't need any fencing along the river because these cows can't swim. They don't have little floaties attached. I'll call this side length X and I'll call this side length Y. Then the area inside here is the thing I'm trying to maximize, so that needs a name too. I don't need a different variable for this side because it's a rectangle. So this side is the same as this side over here. They're both X. I don't need a variable over here because I don't even have any fence over there. That's along the river, so I don't even care about that side. I know we have 2,400 feet of fence. And clearly, if I'm trying to enclose the most amount of area, I should use all the fence. That should be intuitively clear. That means that the perimeter here has to add up to 2,400. So what is the perimeter here? In terms of the variables X and Y, how much fence do I have in this picture?
X plus Y.
Well, X, so I have X here and Y here. I didn't hear the first part, maybe you said it. There's also an X over here, right? So I've got two side lengths of X and one side length of Y. If I didn't have the river here, I would need two Y, right? Because there would be a Y here and a Y here. So if I've got 2,400 feet of fence, and I know I also have 2X plus Y feet of fence, that means 2,400 has to be equal to 2X plus Y. This equation is what we call the constraint. The thing I want to maximize, the area, is just X times Y, right? Like, length times width. This is the quantity we want to maximize. So our goal, the language we use here is we want to maximize this subject to this constraint. So how do I do that? Well, if I want to maximize a function, normally I would differentiate it, set the derivative equal to 0, find critical numbers, min, max, number line, blah, blah, blah. The challenge is that this right now has two different variables. And I can't assume that Y is a function of X here. Y is not implicitly a function of X here. These are independent side lengths. They don't depend on each other. And they're not changing over time. I want to know how the area changes as these side lengths change. So to do that, I need to rewrite A as a function of a single variable. To that end, I'm going to solve my constraint for one variable, say Y, and then substitute that in here. So we begin by solving the constraint for one of the variables. Here I'll say for Y. 2,400 equals 2X plus Y is equivalent to saying 2,400 minus 2X is equal to Y. And now I'll substitute this into my area function. So that area function is a equals x times y. That's x times 2400 minus 2x. And at this stage, I like to switch to writing this in function notation. I would call it a of x, right? It's the area as a function of the side length x. To remind myself or emphasize the fact that we now just have one variable. And also I'll clean this up. So this is negative 2x squared plus 2400 times x. Everybody with me so far? All right. So what I want to do is find the max of this thing. I want to maximize this function. To do that, I'm going to take its derivative. A primed of x. This is going to be negative 4x plus 2400. So a of x is equal to 0 if and only if negative 4x plus 2400 is equal to 0. And that means that 2400 should be equal to 4x. And that means that 600 is equal to x. Oops, sorry, you can't see that, can't be there. So I found this critical number for this area function. I want to verify that this area function really does have an absolute max at x equals 600. To do that, I'm going to make a number line. There's a little theorem I'm going to share with you later that will kind of guarantee for us that we found absolute maxes when we want them, or absolute mins when we want them. But here's my number line for a primed. Maybe I'll put a little divider here. Drop 600 over here. As you're using test points to make your number line for a primed, to find mins and maxes, it's important that your test values are reasonable values in the problem. So like to the left of 600, I wouldn't want to test -5. That would be silly. I cannot have a pen whose side length is -5. I wouldn't really want to use 0 either, right? Because a pen with side length 0, that's not relevant to this problem. It's not something that's going to give me information. So I would test something silly like x equals 1. As long as it's to the left of 600 and bigger than 0, I'll be happy. A primed of 1 is 2400 minus 2 times 1. So this is just 2400 minus 2, which is 2398. In particular, it's positive. So my area function is increasing everywhere to the left of 600. And if I test over here, 601, then a primed of 601 is probably easier to see from here. What are we going to get? A prime, sorry, where are we? Oh, wait, yeah, I plugged into A here. We need to be plugging into A prime. It's not 2398. It is still positive. But A primed of 1, when we come back here and fix this, would be 2400 minus 4 is 2396. It's still greater than 0, but I plugged into the wrong function. A primed of 601, if I plug 601 into this, I'll have -4 times 601, which is -4 times 600 is 2400. So that's 2404. So this would be negative 2404 plus 2400. That's -4, which is less than 0. So over here, my derivative is negative, which means I'm decreasing. So what we found here is a max. But how do I know that it's an absolute max? This is the theorem that I'm going to introduce in a little bit. I'll show it to you. But if you imagine you have a function that's increasing everywhere to the left and decreasing everywhere to the right, it doesn't ever turn around and do anything else. If you're always increasing and then always decreasing, this is not just a local max, but it's also an absolute max. So this is the guy I'm looking for. X equals 600. Hammy, be good, Bubba. It's okay, just be good. Is the absolute max of this function. And this shouldn't be too hard to think through in your head also. This function is a quadratic function. Its graph is a parabola, it opens down. So the shape of the thing is like this. It always looks like this, which means the only max there, it has to be the absolute max. Therefore, the area function a of x has absolute max when x is equal to 600. So that's one of the dimensions. They wanted us to say what dimensions maximize this area. I also need to say what y is. And when x is equal to 600, we know that 2400 is equal to 2x plus y. So we have 2400 is equal to 2 times 600 plus y. Hammy, no, Bubba. No, you can't do that. This is the same as saying 2400 is equal to 1200 plus y. And we can subtract over the 1200 and we get 1200 equals y. So the dimensions that maximize this area are 600 units like this, 600 feet, and 1200 feet like this. And that's it. That's your first applied optimization problem solved. Any questions on what we did here?
Yeah, so what if you only are able to find while solving that you find a local max and not the absolute max, then you get the question wrong. Then what if you how would you be able to find like the absolute max, not the local max?
Yeah, so I think I understand the question there. How do you, like, among all the possibilities, how do you ensure you're finding the absolute max? It's true that not every function has an absolute max. But if the problem is well formed, then there must be the thing that you're looking for, right? Whether it's an absolute min or an absolute max. If the problem has a solution, then that thing must exist. So you shouldn't ever encounter a problem that asks you to find this thing, and then that thing doesn't exist. So I think a kind of enhanced version of that question would be, how do I know that I've found an absolute max or an absolute min? And that's what the theorem I'm about to show you addresses, or one of the things that the theorem I'm about to show you addresses. But the kind of easy sleazy way to think about it is, if you're always increasing to the left of this thing and always decreasing to the right of this thing, then this thing must be an absolute max. And if you turn that over, if you're always decreasing here and always increasing here, then this must be an absolute min. So let me show you the theorem, and then we'll talk about some other possible cases and where you might need to be careful regarding that issue. Yeah. Suppose x equals c is a critical number for the function f of x, then if f prime of x is less than 0 for all x less than c, and f primed of x is greater than 0 for all x greater than c, then f of x must have, let's see, if f prime is negative everywhere to the left and positive everywhere to the right, that means you're decreasing everywhere to the left, increasing everywhere to the right, must have an absolute max, or sorry, an absolute min at x equals c. And sort of the other side of this is if f primed of x is positive for all x less than c, and f primed of x is negative for all x greater than c, then f of x must have an absolute max at x equals c. So this is sort of one, maybe a half answer to that question. It's the thing that you're going to use for the most part in these problems. So if your function is always decreasing to the left of c and always increasing to the right of c, then c has to be the location of an absolute min. And conversely, if f is always increasing to the left of c and always decreasing to the right of c, then you must have an absolute max. But there are other possibilities. Some other things having to do with mins and maxes that you might want to recall from section 4.1 is that if you have a continuous function on a closed bounded interval, then that must have an absolute max and must have an absolute min. Got to have both. So if your domain is restricted, and generally the domains here are restricted. If we look back at this, I haven't said it explicitly, but there is a finite interval that x can run through for this function. X has to be greater than or equal to 0. And since the total amount of fence can't exceed 2400, x has to be less than 1200, right? Even if y is 0 here, then x is 1200. So really your domain here, you're maximizing this on the domain 0 to 1200. So this is a continuous function on a closed bounded interval. So it must have an absolute max. It also has an absolute min at 0, but it must have an absolute max. So there will always be an absolute min or an absolute max, whatever the thing is that you guys are looking for on these problems, because they're well-designed problems. But other stuff you should kind of be aware of. Absolute mins and maxes can be a little bit tricky. If your domain isn't restricted at all, it's still possible to have both of these. The function I'm drawing here has an absolute max and an absolute min, even though it doesn't have a restricted domain, right? This would be the absolute max. And this would be the absolute min. So even if you don't have a restricted domain, it's possible to have both. And you just kind of have to be careful. Thinking about the graph is the ideal way to do this. And let me see, did they graph a of x here? No, they didn't. But let me do that for you. Our function a of x in this last problem was -2x x squared plus 2400x. Zoom way out. Big love heart. All right, let's rescale this. So 0 to 1200, because that was our restricted domain. And 0 to, I don't know, 500,000. Ah, shit. So there we go. So here's the function a of x, and this guy definitely does have an absolute max. If we restrict to the interval 0, 0 less than or equal to x less than or equal to 100, he also has an absolute min, right? The absolute min is 0 and it occurs here and here. But the thing we're looking for was this. So part of this is trusting the theorem, and part of it is being comfortable with the geometry and thinking about graphs. If you're ever unsure, that's really what this number line business is for, right? That's the purpose of the number line here, is to kind of help us be confident that we're finding the thing we want to find. If the picture was more complicated than this, like you had 2 local maxes, then you would want to make sure of a few things. It's certainly possible to have no absolute min and no absolute max. If you have a function like this. Here we have a local max. And here we have a local min. And I know one of the things people are often tempted to say is, well, the absolute max should be the biggest of all the local maxes. That's not necessarily true. Here, there's only one local max, so this is definitely the biggest local max. But because the arrows go up on this side, it's not an absolute max. There are many points on the graph taller than this. And the same thing is true about the local min. This is not an absolute min because the arrow goes down like this. The applied optimization problem should never give you a function looking like this. If this were the case for the function you were trying to minimize or maximize, there would be no solution. And then what's really the game changer here, what really saves us, is that in practice, these functions always have restricted domains, right? I never actually have an infinite amount of material to play with. In real life, you don't usually have anything like an unlimited supply of whatever. So there's always going to be some sort of restricted domain, which means the techniques of section 4.1 are going to be relevant here. So if you wanted to find the absolute min for this function, you would first locate the local mins. This is a local max. So you would do the number line thing to find all the local extrema. But then you need to check against the values of the endpoints. So your local min here, this turns out to be an absolute min. This local max here, though, is not your absolute max. Your absolute max is over here. So in theory, is it possible to construct a problem like this that doesn't have a good answer? Yeah, in theory it is. But if you take that problem and you make it subject to the constraints of the real world, you'll always have an absolute min and an absolute max, because I never have an infinite amount of fence. I never have an infinite, whatever volume. I never have any of those things being infinite. So your domain will always be finite. You'll really always be in this situation. But sometimes it might feel like you're in this situation, or you don't want to do the work to find the restricted domain. And the number line will save you in pretty much all of those cases. But if you're ever in doubt, look at the graph. Okay. I'd like to look at a couple more problems like these. So let's do that. If you want to, I solved that farm problem and this oil can problem with my earlier class. So just like you can look at the videos that I posted. Oh, let me say this. I posted links to both videos from Monday's class. So you can see the example I worked with them for the curve sketching, as well as the example I worked with you guys. And we'll do the same thing for today's, so that way we get a maximal diversity of examples. Here's the the theorem that I stated, right? If f prime is positive everywhere to the left of C and negative everywhere to the right of C, then you've got an absolute max there. If f prime is negative everywhere to the left of C and positive everywhere to the right of C, then you've got an absolute min there. It is possible to escape here using implicit differentiation. I really don't suggest that. These problems are fun, but they're not really applied optimization. These are more math problems. So let's do 15. This is start as a challenging problem. So they want us to begin with 1200 cm squared of material to make a box. The base is going to be square and the top is going to be open. We want to maximize the volume. So an engineer, come here, has 1200 square centimeters of material to make a box with an open top and a square base. Same sort of thing, we want to find the dimensions to maximize the volume. Of the box. So kind of like our related rates problems, we want to draw a picture, label things with variables where they're needed, and then use the geometry to write down some equations. So I'll do my best to draw this box. I'm told that the top is open and the base has to be a square. All right. So if the base is a square, then this side length and this side length have to be the same. And these guys also have to be the same. I'll call that X. The height here, we can call this Y. And so the volume of the box is, length times width times height. That's X times Y, or just X squared times Y. The surface area of the box that's the amount of material I have to play with. So on the one hand, that has to be 1200. But on the other hand, how much material do I have here? Well, the base is an X by X square. So that's X squared. Each of these sides, there's 1, 2, 3, 4 sides, and each one of those is X by Y. And then the top is open. There's nothing for the top. So again, this is the quantity to maximize. and this is my constraint. So I want to maximize this function subject to this constraint. Again, the thing I want to maximize is a function of two different variables. So in order to make this happen, I need to first solve this for one of my variables, plug that back in here, and get myself a function of a single variable so that I can differentiate, find mins and maxes. It is sometimes possible to use implicit differentiation here, but I really don't recommend it. I think it's much simpler if you just solve the constraint and plug back in. So let's solve this for y. We could solve for x, but in this case, solving for x is a little bit gnarly because I've got an x squared and an x term. It's not going to be as pretty. So that's the same. I have 1200 plus x squared. I'm sorry, 1200 equals x squared plus xy. So 1200 minus x squared equals xy. So 1200 minus x squared over x is equal to y. And I'm going to plug this in to my volume equation. What is that going to look like? That's going to look like v equals, well, it's x squared times y. So if I plug in for y, 1200 minus x squared all over x, that looks like this. I'll rewrite this in function notation again to emphasize that it's a function of a single variable, and I'll also clean it up. The x squared up here can cancel with the x down here, and I'll get x times 1200 minus x squared, which is the same as saying negative x cubed plus 1200x. So that's v of x. That is the volume as a function of the one side length, with the understanding that the surface area has to be 1200 cm squared. Now I need to find critical numbers. I want to maximize this thing. So we'll take v primed. V primed of x here is the derivative of this. That's negative 3x squared plus 1200. And this is a polynomial, so the only critical numbers are going to come from setting this equal to 0. So that means 0 has to be equal to negative 3x squared plus 1200, which means that 3x squared has to be equal to 1200, which means that x squared has to be 400. So technically I have two possible solutions here. X is equal to 20 or negative 20. Those are my critical numbers. But I know that I'm talking about a volume here, and I'm talking about a side length. X is a side length. So, okay, yeah, let's come back and look at the surface area really quick. Sorry, so I got a question in chat here. How do we get the surface area? I'm keeping in mind that this box is open on the top, and I'm just looking at the area of each of these little pieces. So the area of this side right here is x times y. The height is y. And then there's 1, 2, 3, 4 of those. Oh shit, did I fuck up? I did. I'm so sorry, guys. Yeah, Kevin caught me, and he caught me just in time before this went really off the rails. The base is x squared, so this has area x, y. This, and the back piece all have area x, y. So this really should be 4xy. I apologize for this, guys, but we are going to have to go back. All right. My surface area here should be x squared plus 4xy. So yeah, we're going to solve. So go ahead. I know this sucks. Scratch all this. I know it sucks, but better than going back and trying to repair it. Answer to your question, Kevin, there's 1, 2, 3, 4 of these sides, and they all have area xy. There's one base down here. He has area x squared. So the surface area is 1200. That's the surface area they gave me, equals x squared, the base, plus 4 copies of x times y. So I'm going to solve this constraint for y, and that will give me y equals 1200 minus x squared over 4x. I'll plug this in to volume equation. Because they told us that the base is that this box has a square base, right? So Tara asks, how do I know that the base here has area x squared? It's coming from the problem. They told me that the base of this box is square rather than just like an arbitrary rectangle. So that means every side length along the base has to be x. So yeah, the two things that are free to choose here, I can choose the side length of the square base, and I can choose the height. But the base has to be a square, so each of those side lengths has to be the same. So if I take this back to this step, and I plug this into my volume expression, V is equal to x squared times y. Y is 1200 minus x squared over 4x. We get that v of x as a function of a single variable. You cancel the x's again. You'll get x times 1200 minus x squared over 4. I'll bring the 4 out front as a 1/4. And when you clean all of this up, you'll get negative 1/4 x squared. And then 1200 over 4 is 300. So plus 300x. All right, so this is v of x. I trust that we did this correctly now. Yes. All right. Now we'll differentiate. And find critical numbers. So v primed, the derivative of my volume equation here, will be negative 1/2 x plus 300. So setting this equal to 0 means we'll have 0 equals negative 1/2 x plus 300, which means 1/2 x equals 300. Oh, look at that. That's funny. So x is 600 again here. This is just a silly coincidence. Oh, thank you. Thanks to all of you who helped correct the error. So our only critical number for v, the only place where v primed is 0 or undefined, is at 600. So on my number line, I just place 600 here. And I can test something to the left and something to the right. If I test x equals 1, over here, v primed of 1 is -1/2 plus 300. That's 299.5, which is certainly a positive number. So the volume is increasing until we get up to x equals 600. But then as soon as x gets bigger than 600, let's test x equals 601. V primed of 601 would be -1/2 times 601. That's 300.5, or sorry, -300.5 plus 300, which is -0.5, -1/2. So that's negative, and that means my volume starts decreasing. 600 is an absolute max. How do I know it's an absolute max and not just a local max? Well, everywhere to the left of 600, this function is increasing. And everywhere to the right of 600, this function is decreasing. And that's our theorem, right? So you can kind of rely on that theorem. Since f primed is positive everywhere to the left of 600 and negative everywhere to the right of 600, this local max has to also be absolute. So v of x is maximized when x is equal to 600. Now we need to find y. We can plug x equals 600 into our constraint. The constraint is the 1200 equals x squared plus 4xy. So that's 1200 equals 600 squared plus 4 times 600 times y. And we'll solve this for y. Actually, I think I already had a version of it solved for y. That's okay. So this is 1200 equals 600 squared, which is, I think, 36,000, 360,000. Plus 4 times 600 is 2400. Y. I'm a little bit nervous here. This seems to be saying that y is going to come out to something negative. Did I look something stupid up here? Why am I nervous? It's over. 2, 600. I write down the constraint correct here. X squared plus 4 copies of xy. Nala, no kitty. Yeah, this definitely will give us something negative. Give me 1 second. -100 minus x squared divided by 4x. That would be this. So put it in here. So this is 1/4. Oops. Oh, god damn it. I can't trust my brain anymore. Correct. This looks correct. So this would be 1200x minus x cubed. I'm so sorry, guys. I'm having a rough day today. How do I do this without ruining the lecture? This should be an x cubed, right? X times x squared. really hate to do this to you guys, but we're gonna have to go back and run through this procedure one more time. My head's just not on straight today. It happens like this, you make a mistake and then get nervous and it makes it harder to keep your head straight. So we'll continue from here. I'm so sorry. Yeah, so this is going to make this a teachable moment, right? If somewhere along the course of your problem solving, you find something that doesn't make any fucking sense, like you realize the solution to this equation would be negative, you know you made a mistake somewhere. So I start tracing back to see where that mistake could have been. There's no reason to waste this opportunity. Definitely, we subtract 360,000 from both sides here. This should not, this would be a negative number. You divide a negative number by a positive number, you get a negative number for y, which means that this 600 had to be wrong, right? If this 600 leads me to a negative y value, then the 600 had to be wrong. So we start looking back for a place where there's a mistake, and the mistake is right from here to here. I wrote this, when I simplified this, I wrote -1/4 x squared plus 300x. The issue is when you distribute this x, you're going to get 1200x minus x cubed, not x squared. So that was the mistake here. So this should be 1200x minus x cubed all over 4. That's -1/4 x cubed plus 300x. So if we come back here and differentiate this again, it looks like Ben might have, yeah, the derivative that we need there, v primed of x, which would be -3/4 x squared plus 300. And now this fellow, if I set this equal to 0, I can subtract the 300 over, -300 equals -3/4 x squared. And then I can multiply by 4/3. So that would be -1200 over -3 equals x squared. -1200 divided by -3 is -400. Or sorry, positive. Fuck me, positive 400 equals x squared, which means x has to be one of positive or -20. That is much more in the range of values we should be looking at. I know that I'm not interested in -20. That doesn't make sense in the problem, because x is a side length. So I can go ahead and set up my number line for v primed. The 0 is a lower bound on the reasonable values for x. Oh, no, that's okay. I appreciate it then. So I'll need to test something between 0 and 20 here and something to the right of 20 here. If I test x equals 1 over here in v primed, then I'll have 300 minus 3/4. V primed of 1 is 300 minus 3/4, which is definitely a positive number. So we're increasing everywhere over here. And if we test x equals something like 21 over here, v primed of 21 is -3/4 times 21 squared plus 300. 21 squared times 21 squared is 441. If you multiply this by 3/4 or -3/4, that's -0.75. You get 330. And if you add that to 300, you get negative 30.75, which is certainly negative. So this has to be a local and absolute max, which is good news. And then finally, find y. We sub x equals 20 into the constraint. So going back and substituting 20 into our constraint equation, the constraint equation is our 1200 equals x squared plus 4xy. So 1200 is equal to 20 squared plus 4 copies of 20 times y. That's very sweet of you, Julio. I appreciate it. Yeah, mistakes do happen, and as long as you guys are getting something out of it, I wouldn't consider it a total waste of lecture time. But I also apologize because I shouldn't be as frequent as they have been here. So we just clean this up and solve for y. The square of 20 is 400. 4 times 20 is 80. So we subtract the 400 over 1200 minus 400 is 800. So 800 is equal to 80y. And then divide both sides by 80 and we'll get y should be 10. So the dimensions that maximize this box are a square base of side length 10, of side length 20. X equals 20 is our x value, and a height of 10. So the box would be a little bit bigger on the base than it is tall. It's going to be kind of fat and short. This would be 10 by 10. I'm sorry, 20 by 20. And then our height here would be half of that. And you'll notice that a lot of shipping boxes, right? You go to the post office or FedEx or something. Most of your shipping boxes have this sort of geometry. They're kind of squat and wide. And it's because it's the more efficient way to do this. So each of these is 20, and this height is half of that is 10. All right, I'm sure I've burned up most of the time. So is there anything else that we want to talk about here? I don't have anything else planned for you guys. The applied optimization stuff, these are fun problems. Is there anything else here that looks like a challenging setup? Maybe we can look at one of these straight math problems. These are cute. Finding the area of the largest rectangle that can be inscribed inside a semicircle of radius r, or finding the distance. Yeah, I do like these. These are fun. But maybe I'll hold off. I don't think I can get through any one of these in the 6 minutes we have remaining. So I think I'll probably go ahead and call it here. Yeah, that is all I have for you guys today. I'm going to go ahead and drop the study guide and final homework for you guys today. And that way you can go through and start working on some of these problems. There'll be curve sketching and applied optimization in there. And then make sure you spend some time working on the study guide over the break. I will go ahead and also open up the Discord for your class. That way you guys, I'll post something like a link to a Discord server. So you guys, along with my other Calc 1 students, can ask questions and communicate with me a little bit more conveniently over break. Well, yeah, that's it. I hope you guys have a lovely rest of your day. If you do need to talk about anything, you can come see me in office hours. Otherwise, my next contact with you will be on the day of your test when you come back from break. So remember, we do have that test on the day you come back. Please be prepared for that. And remember, you'll have to sign into Zoom on your phone. I'll give you the okay, throw you into a breakout room, and then we'll get started on the test. But between now and then, just make sure you're solving lots of problems, get as prepared as you possibly can. And I'll make an announcement about office hours over break. I do intend to hold at least one, maybe 2 office hours over the break, so you can come and ask questions there too. No, we will. We'll have class on Friday. So Friday is our review. Remember, Friday is our review class. Oh, I said, yeah, we wouldn't see each other till break. No, that's, yeah, I apologize. We will see each other on Friday. Friday is our review. But yeah, that is it. Take care, guys.